Hey, are you guys ready for the pool yet? It's almost summertime. It's summer in the southern hemisphere? Crikey, it was way off. Hey everybody, Dave here. Today's video is about why we have seasons here on Earth. So let's go ahead and get started by testing your seasons knowledge. Which of these four images most accurately shows the shape of the Earth's orbit as it goes around the sun? And the answer is C. But please don't feel bad if you get this wrong. If you Google Earth's orbit around the sun, most of what pops up is either misleading or incorrect. It turns out that the Earth's orbit is by far closest to a circle, but it's technically an ellipse. On average, we're 93 million miles from the sun, but at our closest, we're 91 million miles, called Perihelion for you science geeks, whom I love. And at times, we're 95 million miles from the sun, called Aphelion. Which brings me to my second question. At what time of the year is the Earth closest to the sun? Is it the first week of A, January, B, April, C, July, or D, October? And the answer is January. Confused? Don't be. It's simple. The distance between the Earth and the sun is not the cause of seasons. To hammer this fact home, if the distance was the cause of seasons, then the entire Earth would be experiencing summer at the same time, and the whole Earth would have winter at the same time. But we don't. While it's summer in the northern hemisphere, in the southern hemisphere it's winter. And now for the amazing science questions of the day. Number 1, which planet in our solar system has seasons most similar to Earth's? And number 2, which planet has the most extreme seasons? Stay tuned for the amazing answer. Now let's recreate what's happening to cause seasons here at home. I'm going to model what really causes seasons using a light meter app on my phone and a globe of the Earth in my backyard. And I'll take measurements of how much light energy is hitting the Earth all the way from the equator up to the North Pole. At the equator, the light is hitting my phone directly, at a 90-degree angle. Imagine a tiny person standing on the equator. To them, the sun would be directly overhead. So that's where I'll begin. With my assistant Theo, I take a reading of light energy at the equator, then move up to the Tropic of Cancer at 23.5 degrees north latitude, up to Boise, Idaho at 45, the Arctic Circle, and finally the North Pole. Now let's take a look at the results. As we go further north, the amount of light energy goes down. At the equator, where the sun's at 90 degrees directly overhead, there's 800 lux of light energy. And at the North Pole, where the sun is on the horizon at 0 degrees, there's only 10 lux of light energy. Here's the thing though, that data was for an untilted Earth. In reality, the Earth is tilted 23.5 degrees off its vertical axis. Sometimes the northern hemisphere is tilted toward the sun, and sometimes it's tilted away from the sun. So I collected data for those scenarios as well so that we can compare our results. And here are the results. The red line on this graph represents how much light energy is hitting the Earth's surface at different latitudes when the Earth is tilted toward the sun. The blue line is when there's no tilt, and the yellow line is when the tilt is facing away from the sun. There's a huge difference. There's way more energy hitting the northern hemisphere when the Earth is tilted toward the sun, as shown on that red line. You can see that as the northern hemisphere is tilted toward the sun, sunlight is hitting the Earth at a 90-degree angle north of the equator, at the Tropic of Cancer. At the North Pole, it's hitting at a much lower angle, about 23.5 degrees, but it never goes onto the night side of Earth, giving it 24-hour-long days. We in North America also get much longer days, as we are on the day side of the Earth much longer. When the tilt of the Earth is leaning away from the sun in the northern hemisphere, sunlight is hitting the southern hemisphere at a 90-degree angle, and they are having much longer days. It's summertime in January. But the North Pole, it doesn't even reach the day side of Earth, and North America has a very low angle of light, and quite weak. And light striking a surface at 90 degrees and being so incredibly strong explains a lot of things you see in your daily life, like why you're so fast to sunburn on your shoulders and the tops of your ears, why people place solar panels facing the direction they do to generate electricity, why ski resorts are typically found on the north sides of mountains when the sun is in the south. So to summarize, seasons are not the result of the distance between the Earth and the Sun. The tilt of the Earth results in the Sun being higher in the summer and lower in the sky in the winter. It also changes the length of days for those time periods as well, which in combination give us our different seasons. So there you have it. The mystery of the seasons has been solved. And the answer to the science questions of the day, first one anyway, is Mars. Mars has a tilt very similar to Earth's and therefore has seasons really similar to Earth's as well. In Mars' summer, you could almost even live there. And the answer to the most extreme seasons on Earth is Uranus. Uranus' tilt is at 90 degrees. It rolls along in its orbit as it goes around the sun. It's pretty crazy and extreme. I hope you enjoyed this video. And if so, please like, subscribe, and leave a comment. Have a great season, wherever you are and whichever one it is.